The customer mentioned that this PCB has an F1 error. When I tested it, here's how I proceeded. First, I installed its reactor. Then, I connected the main supply, attaching the neutral wire to the neutral terminal and the line wire to the line terminal. We ensured all connections were proper. After that, I supplied power directly to the PCB. On this PCB, there are LEDs 1, 2, and 3, which should light up and then turn off. This indicates that the PCB is active and F1 error can be detected. However, at the moment, this PCB is completely dead. None of the LEDs are lighting up or blinking. While the customer reported an F1 error, further analysis revealed that this PCB actually has an E5 error. Now, I'll disconnect the power supply and remove the switch for safety. Since we supplied direct power to the PCB, we will first discharge the capacitors. Using a resistive load, I have discharged the capacitors. Next, we set the multimeter to diode mode and started testing the IPM. We connected the negative probe to the negative terminal and the positive probe to the positive terminal of the IPM. Initially, there was some voltage drop, but then it stabilized and disappeared. In such a situation, there's a chance that the IPM is working fine. However, when we checked the U point, it displayed 0.00, which indicates that the U point is faulty. Moving on to the V point, there should be no voltage drop, and similarly, the W point should also show no voltage drop. But since the U point is faulty, it means the issue is caused by the IPM. Now I'll remove the reactor and then take out the PCB by unscrewing all the screws. The PCB has been removed. In situations where the PCB shows an F1 or E5 error, it is crucial to test the microcontroller to ensure it isn't shorted. If the microcontroller is shorted, further repairs, like replacing the IPM, will not resolve the issue because the problem will persist. Testing the microcontroller is essential. To test the microcontroller, I'll use a multimeter set to continuity mode. Typically, if the microcontroller is shorted, the capacitors connected to it, like C18, C29, C89, and C105, will also be shorted. By checking these capacitors, we can determine if the microcontroller is faulty. Here's how I tested. I checked the first capacitor, and there was no beep sound. On testing the second capacitor, a continuous beep sound was observed. Similarly, the third capacitor also gave a beep sound. The last capacitor didn't produce a beep sound. Since two capacitors are giving a beep, it indicates that the microcontroller is 90% likely faulty. Next, I'll test the ZD7 diode located near the microcontroller. Using the multimeter in diode mode, I checked across its terminals. If the reading is 0.00, it confirms the diode is shorted, which further indicates the microcontroller is also shorted. This process confirms whether the issue lies with the microcontroller. Apart from the microcontroller fault, it is also possible for the issue to lie within these capacitors. These capacitors are crucial for stabilizing the voltage supplied to the microcontroller and IPM, ensuring that the negative supply remains stable and filtering out any noise or fluctuations. This stability is essential for the proper functioning of the microcontroller and IPM. To rule out capacitor-related faults, we also need to test their continuity. After testing all the capacitors in continuity mode, none of them produced a beep sound, which indicates they are likely in good condition. However, the two capacitors connected to the Zener diode ZD7 and the Zener diode itself were found to be short-circuited. This confirms that the microcontroller is 100% shorted. In this situation, quick action is required because the IPM's U point is shorted. To proceed, we need to cut the IPM. The low side pins have been cut. Once the IPM was removed, it was clear that it had burnt out, and due to this failure, the microcontroller also got damaged. In this case, we must check the IGBT in diode mode, as a faulty IGBT would also continue to cause issues. When I connected any probe to any point, the multimeter showed 0 in all cases. which means the IGBT is also shorted. Next, I checked the diode, and it showed a voltage drop of 0.367 volts, which indicates that the diode is good and functioning properly. Finally, I tested the bridge rectifier to ensure there were no short circuits. After changing the polarity, the readings on all points showed OK, confirming that the rectifier is not causing any issues. First, we will mount the circuit board into the holder. The first step is to soften the points and add solder to both sides. So I will add some new solder to soften the pins. One of my viewers asked, why don't I cut pins closer to the IPM? And I'd like to clarify, the longer the pins are, the more difficult it becomes to heat them, while shorter pins are easier to heat. But I will definitely try the method that Sparky told in some future video. Some pins have come up on the other side, so we will remove them from this side. All the pins have been removed now. I am removing the circuit board from the holder again. In the same way, we will also remove the IGBT from here. The number of the IGBT is 50JR22. All the pins of IGBT and IPM are completely clear and clean. Both the IPM and IGBT have been successfully removed. However, there is still some work remaining, and that is to check the microcontroller once again to confirm if it is still short-circuited. This is essential, since the IPM and IGBT were previously short-circuited. It is possible that they are causing the microcontroller to show a short circuit. However, if the microcontroller still shows a short circuit, even without the IPM and IGBT, then it will be necessary to replace the microcontroller. And someone has already worked on this PCB before, and this is a 5-volt voltage regulator, which has been removed, and its ground side has been moved to the top. Now we will confirm whether the microcontroller is actually short-circuited or not. For this, we will use the multimeter again and test it in continuity mode. So the capacitors present here were showing a short circuit. Let's check them again. The first capacitor is showing short circuit. The second capacitor is also showing short circuit. This one is also short circuit. This capacitor should also be short circuited. Not sure why it's not showing, but these 3 capacitors are showing a short circuit. It confirms that the microcontroller is shorted. Therefore, we will need to remove the microcontroller from the PCB. First, we need to remove the silicon from the top of the microcontroller. I will apply paste to all the points around the microcontroller. This will soften the solder, making it easier to remove. I'll also add some extra soldering to the points. And then use the hot air blower to heat the area and complete the work. After removing the microcontroller, we need to confirm if the short circuit in the capacitors has been cleared. To do this, I checked again in continuity mode and found that none of the capacitors were producing a beep, indicating that the short circuit in the capacitors is gone. Next, I checked the diode in diode mode. The voltage drop showed a reading, and when I change the polarity, the voltage drop will be lower. The reading right now is 0.471 volts, which indicates that the diode is functioning properly and there is no short circuit present. This voltage regulator had been lifted from the soldering pad, so we will place it back down. To do this, I heated the regulator and fixed it into its proper position. By applying heat, the solder joints were softened, allowing the voltage regulator to be properly aligned and secured back in place. I have new microcontrollers of the same model available for this PCB, so I will remove one microcontroller from here. Now I will apply flux to the MCU's soldering pads. This flux also contains soldering tin. This paste helps with the soldering process and ensures a strong connection. Pin number 1 of the microcontroller will start from this small hole, not the larger hole. So let's go ahead and install this MCU. Excessive solder has accumulated on these pins of the microcontroller. Now we need to remove this excess solder. I will apply flux. After this, I will add some solder to the pins. Now it will be easier to remove the excessive solder. Now I will heat the solder. After heating it, I have removed the excess solder with sucker. I am continuing this process around all sides of the microcontroller, ensuring that any excess solder is being cleaned up and everything is properly aligned. Now, the microcontroller is securely soldered and all points are neat and correctly connected. Now we will test this microcontroller and we will test it in the same way as we did before to check if it is not short-circuited. I will now set the multimeter to continuity mode. So as you can see, there is no continuity on this capacitor. In the same way, there is no continuity on the next capacitor either. No continuity on the last capacitor either. And there is none on this one as well. Here, we will check this diode numbered ZD7 in diode mode. A voltage drop of 0.439 is showing. Let's swap the probe sides and check again to confirm. Now, a voltage drop of 1.056 is showing, which means the short circuit on this diode has been cleared. The microcontroller I installed here is perfectly okay, and the capacitors installed here also need to be checked. I have checked them again, and they are perfectly fine. There is no beep showing on continuity for these capacitors. Now I will install the new IPM. Before installing it, I will show you the IPM number. This is the number of the IPM. You can pause the video to check the number. I will align the IPM with its corresponding holes on the PCB and ensure that it fits properly. This pin is causing an issue. It will be placed into the hole. This pin is also causing trouble. Some of the pins are causing problems. So the IPM pins have seated in the holes. Now I will align the pins in the holes of the high side. Now these pins are also seated in the holes. I have a new IGBT of the same number, so we will install it here. It's done. Now we will remove this PCB from the holder. Before soldering this, we will apply a technique. The technique involves bending one of the pins here and another pin over here. Similarly, we will bend one pin from this side and another from here. In the same way, we will slightly bend the IGBT's pins back and forth. This will ensure that it doesn't fall downwards. Now, we will bring the heatsink and properly place the PCB on top of it. It is properly seated on the heatsink. Here there are 1, 2, and 3 screw holes to tighten the PCB with the heatsink. Now we will insert the screws and tighten them. Now this PCB is secured tightly with the heatsink. Now we will tighten the IPM screws. I have also tightened the IGBT along with it. Before soldering, I will apply flux to the pins. Now we will proceed with soldering it. Before supplying power, we will test the IPM once. We will place the negative probe on the negative pin and the positive probe on the positive pin. When we did this, we observed a slight voltage drop, which then disappeared. This means that the IPM is perfectly fine. Next, there is no voltage drop showing on the U, V, and W pins. Now, I will switch the probe sides, placing the positive probe on the negative pin and the negative probe on the positive pin. Let's see what happens. We now observe a voltage drop of 0.532 here. Let's check the U point in the same way. There is a 0.467 voltage drop here. The same 0.467 voltage drop is observed on the V pin and also on the W pin. This means that all these points are fine, which indicates that the IPM is perfectly okay. Similarly, the final test will be for the IGBT. When the probes are placed on any of the pins, there should be a voltage drop showing. After switching the probe sides, a variable voltage drop is still showing on the pins, and now it has disappeared. This means the IGBT is also fine now. Before supplying power, I will connect the thermistors to their respective connector. Now we will supply power. The supply is turned on, and all the lights are on. The switching has also occurred. Normally, when there is an F1 error, the LEDs show up immediately. However, no LED error blinking is happening, which means the PCB is completely fine. And until now, there has been no problem. It is waiting for the serial communication, and since its connection with the indoor PCB has not been made, it will keep trying. After a while, LED 3 and 2 will become stable, and LED 1 will start blinking. We will wait as well, and here, LED 3 and 2 have become stable, and LED 1 has started blinking. Now, we will perform the final test on this circuit board, and this is a very important test. Without this test, handing it over to the customer may result in a fault going unnoticed. So, I will provide power. After powering it on, the lights have turned on. I will set the multimeter to DC voltage and check the voltages. We are getting 322 DC volts here, which is fine. Let's check the U pin in the same way. Here, we are getting 15 volts, which is perfectly okay. Now, let's check the V pin. We are also getting 15 volts here. The last pin is W, and again, we are getting the correct 15 volts. If there were any fault in the IPM, it's possible that the voltage would not be proper at any of these points, causing the IPM not to work properly. Now it's confirmed that this circuit board is completely okay. There is no issue in it. We can now hand over this circuit board to the customer. Now, this is how the PCB can be given a shine, making it look like a brand new circuit board. I'll show you the shine on the microcontroller, which is shining perfectly. To achieve this, I use this product. By using this, you can enhance the shine of your PCB and also provide waterproofing at the same time. Click on the left or right thumbnail to watch our next videos and subscribe. Thank you.